Now, let us see the next question. 57. Dead load of the beams is W by 2 per meter run. There was a like this was there. Okay, this is the beam and dead load is W by 2 per meter run. This is W by 2. This UDL is also W by 2 per meter. W by 2 per meter. Okay. For this case, we know the Bending diagram. Individual Bending diagrams are like this. WL square by 8. W means W by 2. L square by 8. So you will get WL square by 16. So is the case with this one. Because these two are independent, simply supported beams. Now what he has done, after they have bent, make them come together and you maintain the continuity. Now what happened? It now behaves like this. Now continuity is established. And now you are applying live load. This is dead load. And this is live load. This live load is W by 2 kilonewtons per meter. Okay. After continuity is established, some more load came. Now for this one, we know how the Bending diagram goes. For the second case, W like this it will come. This is a positive bending moment. This is WL square by 16. This is WL square by 16. If you assume it as simply supported beam. Now the negative bending moment here, because continuity is established, we know how to draw this bending moment diagram. How much this value is when continuity is there? WL square by 16. That we have to make it fast. Minus WL square by 16 plus WL square by 16 minus WL square by 16 plus WL square by 16. Then these are the fixed end moments. Release. You have to write plus WL square by 16, half of that plus WL square by 32. Here release minus WL square by 16, half of that minus WL square by 32. So entire story we don't have to write distribution factors are 0.5 etc. We are not interested. This is 0. This is plus 32 common factor. If I take it 2 plus 1, 3 WL square by 32. 3 WL square by 32. This is plus minus 3 W L square by 32 0. So here you will get 3 W L square by 32. That means here half of that means 3 WL square by 64. Then how much is left out here? This is WL square by 16 minus 3 WL square by 64. So 64 common factor, 4 minus this is 4, this is 1, 4 minus 1, 3. 4 minus 3 is 1. So you will get WL square by 64. So WL square by 64. Now the net value midspan moment means here. How much is that value? Net value WL square by 16 plus WL square by 64. Now we are adding this plus this. 64 common, 4 plus 1, 5. 5 WL square by 64. In other words, something we missed. 16 into 4, 4 minus 3, 1. 3 WL square by 16. So you will get WL square by 16 minus 3WL square by 64. WL square by 64. This value is WL square by 64. So WL square by 16 plus this one. So 64, 4 plus 1, 5. You are getting 5 WL square by 64. Let us see where we have made the mistake. Now in this case, WL square by 16, WL square by 16. That's the correct. Now here WL square by 16. This point we have to see minus WL square by 12. This part we have missed it. Fixed end, first you have to fix it. Fixed end moment is minus W means W by 2. WL square by 12. So WL square by 24 minus WL square by 24 plus WL square by 24 minus WL square by 24 plus WL square by 24. So release 24. Now this will become 48 minus WL square by 48. Here also minus. So now you will get this value works out to be so you will get 348 common factor 2 plus 1 3WL square by 48 minus 3WL square by 48. This value is 3WL square by 48. Net value will get WL square by 16 minus 3WL square by 48. 48 common 16 3. This will also become WL 48 common factor 24 into 2. 2 plus 1. You are getting WL square by 16. Here also WL square by 16. This is WL square by 16. Okay. Now we'll continue. I think we can repeat this. There is a small mistake. We repeat. Okay. Now after this continuity is established. For this case, the fixed end moments are like this. MFAB means minus W means W by 2. WL square by 12. You will get minus WL square by 24. Now you see all those moments, if you take the distribution, this is minus WL square by 24 plus WL square by 24 minus WL square by 24 plus WL square by 24. This point is CA, B, C, let us say. Okay, this you have to release. So plus WL square by 24. Carry over moment is plus WL square by 48. Here also you have to release minus WL square by 24. Half is minus WL square by 48. So 0, 24 plus 4. 3 you can write 3 WL square by 48. In other words, plus WL square by 16 and this is minus WL square by 16. So now in this case, when you repeat the same problem, it looks something like this. Okay, this is the free bend moment diagram. WL square by 16, WL square by 16. So the negative end moment also you got it as WL square by 16 minus. So when you overlap it, it will go something like this minus. Now this value is half of that WL square by 32. Now this height will become now WL square by 16 minus WL square by 32. Common factor, if I take 32, 2 minus 1, you will get WL square by 32. So net moment is like this. This plus this one you have to take. This is the net bend moment here. So when you are superimposing them, you will get like this. Plus WL square by 16 plus this net value is WL square by 32. Common factor 32, if you take it, you will get 3 WL square by 32. So 57th question, the correct option is 3 WL square by 32. So 57th, D is the option. Next, 58, axial force in the member AB. We solved it in the class. Axial force in the AB, we got it as 1.5 M by L tension. That means correct answer is D. This is solved in the class. Then 59. A continuous beam ABC is loaded with a concentrated moment. Loaded with a concentrated moment M. End reaction at C is calculated as R0. This is R0. End reaction at C is calculated as R0. A, B, C. VC is R0. Keeping all conditions the same, if the end C is fixed, what is the reaction at C? So now all conditions fixed, same, I am fixing it like this. This is some reaction, we are not interested, VA. This is M, this is C. A, B, C. He is simply asking what is the reaction at C. When there is a moment M, we are getting R0. When hinge support is there, then the spans etc. not given. When you fix it, then what will happen? If you take this free body diagram, let us say, whatever may be the lengths, if I take the free body diagram of MBC alone, if I take it out of M, so some value take it as M1, here it is 0 clockwise, here it is 0. Like this it will come, reaction will come like this. So this value VC is R0. If far end is hinged, it is some value 3 by 4, I by L is the stiffness. Now here you have to take it as I by L. That means the distribution factor here it is more. That means moment taken here is more. Okay. So this is BC. Here some M2, let us say. This value is greater than M1. Why? Because far end is fixed means stiffness factor is more. Its share of your applied moment is also more. M2. Then this value is M2 by 2. Because fixed, both of them are clockwise. Now this reaction VC is now naturally greater than R0. Because we don't know the length, we can only have to guess. Because of fixing, its distribution factor is more. So moment shared by BC member is more. And out of M2, half will be carried over. And both moments are clockwise in nature. So anti-clockwise couple will form. So reaction at C will be naturally more than R0. So you simply have to answer greater than R0. 59C. Next 60. This question we have solved in the class MBC plus MCB. 60th B is the answer. This is solved in the class. Next 61. What is the moment at A for the beam shown in figure? This is carryover moment concept. This is the beam, let us say. Here 24 kilonewtons per meter. Okay, 4 meters, 2 meters. 4 meters, 1 meter. Now this we can equate it to like this. This is equivalent to this one. Remove that load 24 kilonewton down, and moment is 24 into 1 into 1 by 2. WL square by 2 means 12 kilonewtons meter. And there is UDL of W, 24 kilonewtons per meter. Okay. Now this point let us say AB. This is the loading condition. Now you see, first carry over moment you take it. Principle of superposition. Due to 12 alone, carry over moment is m by 2. 12 by 2, that means 6. This is called carry over moment. Then due to fixed end, a cantilever beam subjected to UDL, we know the formula WL square by 8. W means 24. This length is 4. WL square by 8. How much? 16 means 8 into 2, 24 into 2, 48. So clockwise 6, anti-clockwise 48. So anti-clockwise 48 minus 6. MA is equal to 48 minus 6, 42 kilonewton meter anti-clockwise. How you get it? From the principle of superposition. So 42 anti-clockwise is the 61. 42 anti-clockwise. C. He has given minus, okay, whatever way, minus for him may be anti-clockwise. Okay, next, 62. Now let us see the 62nd question. What are end moments MA and MB of the beam shown in figure? If the support B sinks by an amount delta, we have a fixed beam with a central hinge. Let us say this is A, B, this point let us say C. This is A, this length is B. Total length is L. Okay. Now one of the supports sinks by delta. If it sinks by delta, what is the deflected shape? Central, no, it is not central hinge, somewhere here it is there. The deflected shape, because when I am pulling it down, it will go like this. Now this is going up here. Now it should go now like this only. It gets pulled. Here slope is 0. So point of contraflexion happens here. This entire beam will sag, this entire beam will hug. Okay. This total depth is say delta. Okay, it deflects by an amount of delta. Let us say up to here, this value is say delta 1. From here to here, let us say delta 2. Delta 1 plus delta 2 is delta. For this profile, I told you here you will get 3 EI delta 1 by L square. Here you will get, for this one alone, we will go to B dash, 3 EI delta 2 by L square. This I can write it as 3 EI delta 2 means delta minus delta 1 by L square. Okay, now that's what we wanted. When amount delta, what are the end moments? He wants to write in terms of delta 1. Then what is the relationship between delta 1 plus delta 2 we have written? Then the reaction. This can also, delta 1, how to get it? If we take this free body diagram alone, hinge was there, it is deflected like this. MA and MB, both of them are anti-clockwise. Then clockwise moments. So the clockwise couple should develop like anti-clockwise, anti-clockwise. So clockwise moment here and here. The reactions are M by L. Net reaction here you will get 3 EI delta 2 by L square plus 3 EI delta 1 by L square, not L square, this is A square, 3 EI delta 1 by A square. This is 3 EI delta 2 by B square. We can write delta minus delta 1. So 3 EI delta 2 by B square plus 3 EI delta 1 by A square. Divide entire thing divided by L. This is the total reaction. If you want to find say reaction here itself, that of no use, we wanted to find the moment. Moment at B is 0. Here the net reaction, here there is a downward force. If you take only this member, this is say AC. Here you have 3 EI delta 1 by A square anti-clockwise. So clockwise must be, if you take this free body diagram alone, downward reaction must be there. It should be pulled down by an amount of 3 EI delta 1 by A cube. Here also 3 EI delta 1 by A cube. M by L formula, if I take it, this is the formula. And for this one, the upward reaction you will get like this. This is overall. This is going up, but further down it is. This is 3 EI delta 2 by B square anti-clockwise. So clockwise reaction is 3 EI delta 2 by B square by B cube. Upward here, downward will be there. 3 EI delta 2 by B cube. Individual if I take it like this. So net reaction must be 0, downward reaction, upward reaction should balance. So we can write 3 EI delta 1 by A cube must be equal to 3 EI delta 2 by B cube. Okay, this delta 2 we can write it as delta minus delta 1. Okay, so we can now write this as 3 EI delta 1 by A cube is equal to 3ei delta by b cube minus 3ei delta 1 by b cube. Push it to the delta 1 this side. So 3ei delta 1 into 1 by a cube plus 1 by b cube is equal to 3ei delta by b cube. So delta 1 we can write in terms of this one. So 3 cancels out. So delta 1 is equal to 3i cancels out. Delta 1 is equal to delta by b cube into 1 by a cube plus 1 by b cube. This is delta 1. Now the moment there is 3a delta 1 by a square. Ma is equal to 3ei delta 1 by a square. Nothing but 3ei by a square into delta 1 is delta by b cube. So b cube into, if you take common factor, a cube plus b cube by a cube b cube. So in other words, b cube cancels out, a square a will remain. So 3ei a into delta by a cube plus b cube. So this is what you will get, ma value, fixed end moment at a. Ma you are getting 3ei a into delta by a cube plus b cube. Now which option matches? A is wrong, B is wrong, C 3ei delta by a cube plus b cube. Naturally MB will be same, 3ei b delta by a cube plus b cube. So correct option is 62C. So this is what is the process. This deflection profile if you draw one thing, then from here 3a delta 2 by b square you will get. But this one is of no use for us. Finally we realize that this quantity we are not able to make use of this one. But initially we don't know whether it will be useful or not. So this is downward force. There is some upward force also will be there. This is not required. So this and this you should write delta minus delta 1 by b square, we will write it delta 2. Then leave it off. Then separately you draw the free body diagram of AC. This is CB. It went like this, it went like this. This reaction and this reaction, on the AC member downward reaction should be there. CB member upward reaction should be there. Net reaction 0. This must be equal to this. So equate both. They must be equal. So you simplify that delta 1 in terms of delta you will get. Then MA means 3a delta 1 by a square as your fundamental formula. That delta 1 value in terms of delta substitute. So you will get 1. If 1 is correct, the other one you don't have to solve it because only one option is there. So we can match that. So 62C. See, when we are solving the problems for the first time, let us say, some certain calculations may become unimportant, quickly you should come out of it. Then accordingly, finally in 2 minutes time we should break the solution. Next, 63rd. The ratio S by T. S is stiffness of the beam, constant EI at near end. When far end is hinged, this value says S is equal to 3A by L. At the stiffness of a beam at near end, when far end is hinged. To T, stiffness of the same beam at near end when far end is fixed. Same beam when far end is fixed. This is ST. Far end is fixed means we know 4A by L is S by T is asking. So 3 by 4. So 63rd B. 64. The rigid jointed plane frame QRS shown in figure subjected to load P at joint R. Axial deformations neglected. This formula we have solved it. Beta we got it as 7.5. Beta is equal to 7.5. So correct option is A. This one solved in the class. All possibilities I have given you. Then 65. Assertion and reason. For a beam with one end fixed and the other end hinged. One end fixed, other end hinged. When a positive moment M is applied to the hinged end, positive moment, let us say clockwise moment, we don't know what it is. M is applied to the hinged end of the beam. A positive moment M by 2 will be transferred to the other end. Correct? COM. Reason. As the fixed end remains horizontal, and the hinged end does not deflect, correct? Does not deflect. A tangent at the fixed end. A tangent at the fixed end must pass through the hinged end, correct? That is, must pass through the hinged end. That is, the moment of area of the total bend moment diagram, okay, about the hinged end must be equal to 0. So, when you are, this is what you have drawn. So, this is theta B. We have taken deflection when you calculate. Supposing that tangent you have drawn, let us say. Okay. Now, this is the deflection profile. You drop a tangent here, you drop a tangent here. This is the angle between them is given by theta B is nothing but theta is equal to area of the bend moment diagram divided by EI. That the moment of the area of the total bend moment diagram about the hinged end must be 0. That means it is not here we are calculating, here we are taking. If at all, as I have derived this question in the class also, if at all I take it say like this. Tangent, this is theta A is nothing but BB dash by L must be equal to 0. So the reason now we will read again. As the fixed end remains horizontal and the hinged end does not deflect, a tangent at the fixed end must pass through the hinged end. Correct. That is the moment of the area of the total bend moment diagram about the hinged end. So area about the hinged end, that is BB dash is equal to 0. From this theta A is equal to BB dash by L is equal to 0. That means BB dash is equal to 0. That means what? Area into x bar. Ax bar is equal to 0. Moment of the area of the bend moment diagram about the hinged end. So Ax bar you have to measure from B only. About the hinged end must be equal to 0. Same thing. That's what you have taken. From this only you found the carryover moment m by 2. In other words, he is telling you that how to get the m by 2. One end is fixed, one end hinge. When you apply moment m, carryover moment is m by 2. What is the reason for that? Proof. Theta A is equal to BB dash by L is equal to 0 is equal to BB dash is equal to 0. What is BB dash? Moment of the area of the bend moment diagram about B. About B means hinged end. So assertion, reason are correct, and reason is the correct explanation for the assertion. So 65A. Correct explanation also given. Next is 66. The propped cantilever beam shown in bigger figure below is a determinate structure. You see here, there was this is a hinge roller support. There is a hinge here and subjected to some load. Actually, DS is 1 if hinge is not there. Now hinge is there. So R minus S is 4 minus 4, you can take it. So R minus S, 4 minus 4 is 0. So determinate structure. Reason, at the internal hinge shown, there exists a shear transfer. Yes, shear transfer will exist. So that's what earlier problem we have done. Shear transfer, this free body diagram if you draw separately, like this and like this, and there is UDL here. For it not to fall down, there is reaction R, and to balance it, there is a reaction R. So from this beam to this beam, this reaction, shear transfer will be there. Moment, shear transfer, and there exists a shear transfer and no bending moment here. There is no bending moment. Shear is transferring, but bending moment is not there. That is the reason why it became determinate. That fourth additional equation is, what is S4? We are taking sigma x0, sigma y0, sigma m0. Fourth one is bending moment at C is equal to 0. Bending moment is 0, but shear transfer will be there. Shear transfer means reaction will transfer, but bending moment is 0. So assertion, reason are correct. Reason is the correct explanation for the assertion. So 66A. Next 67. The unit load method is useful, correct, for computing deflection, yes, and slope at individual points of a structure. It's correct. Unit load method is a force method of analysis, finding the displacements individual points of a structure. That's what Castigliano's theorem 2 tells us. Then reason. The unit load method is based on the strain energy principle. Based on strain energy principle means that is Castigliano's theorem 2. Okay, at individual points of a structure. So assertion is correct, reason is correct, reason is the correct explanation. Based on strain energy principle means strain energy principle tells you that at any point if you want to find the displacement or slope, you will use the unit load method. So assertion is correct, reason is correct, and reason is the correct explanation for the assertion. Strain energy principle is unit load method is based on the strain energy principle only. So 67 also A. Here reasoning is also correct explanation for the assertion. Both statements are correct, explanation is also same. 68. Method of moment distribution is classified as a force method. Assertion is wrong. The method consists of computing end moments, correct, due to end rotation of the member. Computing end moments due to end rotation of the member. So A is false. Consists of computing end moments due to end rotation of a member. Correct. Reason is correct because if you know theta A and theta B and rotations, if I know MAB, I can find MFAB plus 2EA by L into 2 theta A plus theta B minus 3 delta by L. That means end moment is computed based on the end rotations. Reason is correct, but assertion is wrong. It is not a force method. So A is false, R is true means D is the correct. 68. Because moment distribution method is a stiffness method, it is based on successive approximation of slope deflection equations. Next, 69. D means that only A is false, R is true, correct. The moment distribution method and slope deflection method of structural analysis are essentially stiffness methods. Assertion is correct. What is the reason? Moment distribution method, slope deflections are solved without writing them explicitly, correct? So assertion is correct, reason is correct, but reason is not the correct explanation of the essay. Both statements are correct, that's all. So structural as essentially stiffness methods because you are using the stiffness factor. That's the reason why. But A is correct, R is correct. R is not the correct explanation. Both statements are correct. So B is the answer. Both are correct, but why they are called essentially stiffness methods? Because you are using stiffness factor and carryover moments. Next, degree of fixity at the supports is lessened. Supposing that you have a fixed beam, let us say, subjected to some UDL. You get WL square by 12, WL square by 12. If degree of fixity is lessened, supposing that you make a hinge, say, because degree of fixity now 0, fixed and moment 0. Here, WL square by 8. Compared to this is 50% more. We solved. Now let us see what is the question. If degree of fixity at supports is lessened, maximum hogging moment at the ends will decrease. That means this is also hinge only. Both ends will take it as hinge now. Degree of fixity is lessened. So hogging moments now will become 0. Here hogging moment is more. Maximum hogging moments at the ends will decrease. See, from WL square by 12 to it became 0. WL square by 12 to 0 it became. So assertion A is correct. At the ends will decrease. What is the reason? The degree of fixity at support is lessened. Maximum sagging moment at midspan increases. That is also correct. In this case, you see maximum midspan moment. This is WL square by 8. You get it. In this case, WL square by, if you take both, you got WL square by 24. So sagging moment will increase. Okay. Now that, so both statements are correct. Midspan, if the degree of fixity of supports is lessened, maximum sagging moment at midspan decreases. It will not decrease, it will increase. So bending moment at midspan increases. So statement 2 is wrong. So degree of fixed at support is lessened means sag moment at midspan will increase. First statement is correct. Now let us see. Statement 1 and 2 are individually true, wrong. 1 and 2 are individually true, wrong. 1 is true, 2 is false. 2 is false. So C is correct. 70 is C. Okay. Next. Now we'll see the 71. It's beyond the scope actually. Force in the member AC. Let us try how much time it takes. This angle is 45 degrees. This angle is 60 degrees. We have applied horizontally a load of P is equal to 1000 Newton. This length of the member is a L. A is constant for all the members. So static indeterminacy is R minus S 3 minus 2 1. So this point let us say A, B, C, D. So remove one redundant member AC and replace it by a force X. Then that will look like this. This we are removing, we will remove that hinge here. P is equal to 1000 Newton. Remove this member. This is A, B, C, D. This assume that there is a tensile force X in this member. So X is equal to, formula is this one, minus sigma P K L by summation of K square L. This type of questions in the exam impossible. 2 minutes questions it cannot be given. It is a conventional question paper. Mains exam they can ask you this type of things. P means forces in all members in the determinate structure. K means forces in all members due to unit load placed on the at the joints where you have removed the force. Length of the member by K square L. Okay. So this is L root 2 into L, you will get it. This is 60 degrees means sine 60. Sine 60 is, this is a L by this one. So L by sine 60. This is a X is equal to L by sine 60. So sine 60 is equal to L by X. Sine 60 means L by X. So X you will get L by sine 60. So L by sine 60. We will simplify in the end these values. Okay. Next first point is P values. When load P is applied, we will write here. P values. Hinge supports are there. This is 1000. This is 45 degrees. This is 60 degrees. Okay. This point is A. This point is B. This is C. When I pull it like this is under tension. This is under compression. Okay. This is force F AB you can take. F AC we can take. We can use the sine rule 60 degrees here. That means this angle is 60 degrees. 45. So this is 45. This is the member. So we will use sine rule 45 60. Then what is this angle is 60 plus 45 105. So this is 85. 30 plus 45. 75. Total 180 degrees, 60, 40, 105. So 75 degrees. Now, if you take this force and this angle is 60 degrees, 75 degrees, and this angle we can find 90 plus 45, 135 degrees. Now, if you take sine rule, 1000 Newton is surrounded by 60, 135. Opposite is sine 75. 1000 by sine 75 is equal to FAC is surrounded by 75, 60. Opposite is 135. FAC by sine 135 must be equal to FAB. FAB is surrounded by 135, 75. Opposite is 60. Sine 60. So from this you can calculate forces in both members. FAC is 1000 into sine 75, 1000 by sine 135 by sine 75. FAB 1000 into sine 60 by sine 75. Like this. So force in members you will get. Next, second step, K values. K values means you have to apply unit load. This point say B, A, C. You are taking tension. So 1 here, here also 1. This is of no implication, only this down. 1 down means this will be up, up. This is FAB, FAC. This angle is 45 degrees. This is 60 degrees. So now if I take sigma, this because sigma x0, sigma y0 also we can make it 60 degrees. That means this angle is also 60 degrees. This angle is 45 degrees. So you will get for this one sigma y0 FAB sine 45 plus FAC sine 60 minus 1 is equal to 0. If you write sigma x0 FAB cos 45 minus FAC cos 60 must be 0. Solve 1 and 2. Find FAB, FAC. So P values, K values we find. Stop. Okay. Now FAB, this value 1000 sin 135 by 75 means 732. 1000 sin 60 by sin 75 means 896. K values when you are finding, one is compression, one is tension, because both of them are under compression only, because when I am pulling it, compression will develop like this. 0.517, FAB is 0.517, this is 0.732. So sigma y now it should balance. Next, this is towards the joint means towards the joint, towards the joint. Next we should write a table. PKL by K square L. This I remove now. Now your third step I am showing here. X is equal to minus summation of PKL by summation of K square L. Member P K L PKL, you will get it PKL, then K square, then K square L. Only we have to take two members, AB, then AD, AC. Member AB, P value, member AB is tension positive, again compression negative. Member AB, you got it as tension, AB plus 896. K value is compression, so minus 0.517. Length of AB. The length of AB is root 2 L. That means 1.414 L. So we multiply this value. We will see that. Then AD. AD member we have removed. This is actually D. D member it is. This is C. So AD we will write it here. This is AD. This is also FAD. So FAD is 732. This is AD. Towards the joint, so minus 732. 0.05, that's okay. 732 we will take it approximately. Then AD here towards the joint, minus 0.732. Length is L by sin 60. So L by sin 60, you will get around 1.154. 1.154 L. AC value P is not there. We have removed. No member is there. K value tension 1. So plus 1. Length is L. So this one PKL, it is not there, 0. K square L means L itself. Then here PKL. Here K square means 1 it will become. Then this value 896 into 0.517 into 1.414. You will get 655. 0.01 means 655 will take it. K square means 0.517. You will get 0.267. K square L. So 0.267 into length 1.414. 0.378. Then this one PKL. PKL will become, this value is minus, this is PKL plus, you will get 732 into 0.732 into 1.154, 618. This will become plus 618.3. K square means 0.732 square into 1.154. This value will get 0.618 L. So PKL means you will get it as 655 minus 618, 36.7 minus 36.7. K square L. 0.378 plus 0.618. So 2L, almost 2L you will get, K square L. So X value is minus summation of P K L by summation of K square L. So minus of P K L is minus 36.7 by K square L is 2L. Here 655L like this. So you will get 36.7, 18.35. So force in the redundant member you will get 18.35. So this quantity is sigma pkl, this is sigma k square L. Okay. So 18.35 Newton. Because of the time it is taking, it cannot be a 2 marks question, it is a 10 marks question or 20 marks question. But because in the prelims classes I didn't give you the derivation of this formula also, this question you can neglect. After prelims are over, then you can see this question, but not before. Because this formula, how it has come, I didn't derive, because it is beyond the scope 2 minutes time. But since question is given, some of you who have already completed say this how the compatibility condition comes, those who have completed my mains classes also, there I have explained how this formula comes. So that will be completed. Now you take it for granted that it is beyond the scope in the prelims. Next, now 72nd question, I solved it in the class. I think reaction at B you got it as 60 kilonewton. This is solved in the class. 73, portal frame is given, modulus of velocity, moment of inertia given, rotation in degrees up to 1 decimal place at rigid joint Q. This is the problem. Both ends are fixed. This is Q, yes, R. This is 4 meters, 4 meters. There was a overhang. So moment at Q, if you want to find, clockwise moment plus 1650 kilonewtons per meter into 2 is the total load into 1 clockwise moment minus 2000 kilonewton into 2. So 1650 into 2, 16 into 2, 32, 33. So 700 minus 700 kilonewton meter. That means anti-clockwise. So net moment is 700 kilonewton meter, because the overhang, one is UDL, one is point load. Due to those two UDL and point load, you cut the cantilever off What it does, you show it at Q. Net force is this one. There is a reaction also, but reaction will be taken as axial force. For I, EI value is given. So I value, I value. So out of 400, it will take only 350. This also takes 350. When far end is fixed, how the rotation will be? Like this. He is asking rotation at Q, theta Q. When far end is fixed, we know the formula ml by 4EI. Moment is 350 now, out of 700 it is taking only 350. 350 kilonewton meter. Since everything is in Newton mm square, we will convert it. 350 into 10 to the power of 6 Newton mm into length is 4 meters. That means 4000 mm. ml by 4 E, Young's modulus is 2.5 into 10 to the power of 4. MPM is newtons per mm square. I is 8 into 10 to the power of 8. Okay. So this is the formula. How many zeros are there here? 8 plus 4, 12. So for 12 zeros here, 6, 3, 9, 10. 2 zeros extra are there. So we will write 35, 10, 7, 3, 10 is over. 35 into 4. 4 and 4 cancels. We will cancel it out later. Here 22.5 into 8, 12, right? So 100 we will write. So this much is extra. 4 cancels out. Then 5 sevens, 0.5. So 7 by 80, 40. So 7 by 40 means we can get it as 0.7 by 40. Because calculate is gate question. So 0.175 radian. This is theta q. That's how the, I think it is already solved in your gate booklet. Next 74. A prismatic beam PQR (5 meters, 4 meters). Anti-clockwise moment m 180 kilonewton meter. 5, 4. EI is given fixed quantity 1 into 10 to the power of 4 kilonewton meter square. Rotation at Q up to 2 decimal places. Up to 1 decimal place theta Q, up to 1 decimal place means you have to write 0.18 radian. 0.18 means 0.2 radian you have to write. Theta Q is 0.2 radian. Here 2 decimal places he asked. So you will get, now for m to be 1, we know the formula, both ends are fixed. For theta b is equal to 1, this is theta b, q is there. This is PQR. This what I solved it. For theta b to be 1, how much moment is required? MQ. Moment required is, far end is fixed, 4EI by L. 4EI by L plus 4EI by 4. So 5 common if I take it, 4 plus 5, 9. 9 EI by 5. Then that means for m is equal to 9 EI by 5, theta B is equal to 1. For M is equal to 180 kilonewton meter, theta B how much? Theta B is equal to 180 by 9 EI by 5. So 180 into 5 by 9 EI. This is 20. 100 by EI. 100 by EI has given 10 to the power of 4. All in kilonewton meters. So we didn't change anything. 180 as is we have taken. You will get 0.01 radian. Theta B is 0.01 radian. Up to 2 decimal places means 0.01 radian you will get. Okay. So these are the questions on the methods of structural analysis. Here we have learnt about the Betti's reciprocal work theorem. Also we have learnt all the questions related to slope deflection method, moment distribution method we have learnt in this one. Okay. Next we have trusses chapter. Then again the trusses, there we will learn the method of sections, method of joints, and also matrix methods of structural analysis, where truss analysis we have to consider. Okay, that we will see. Okay, now we'll see the chapter 5, trusses. Okay, first one, maximum number of unknown forces that can be determined in a concurrent coplanar force system under equilibrium. I told you in the method of joints, if you have a concurrent coplanar force system, you can have only sigma x 0, sigma y 0. Sigma m0 will give you 0 is equal to 0. It becomes useless equation. So we have, in method of joints we have seen all forces meet at one point. So we use sigma x 0, sigma y 0 only. So equilibrium equations available are only two. So option A is correct. Then second one, the strain energy stored in member AB of the pin jointed truss. So there was a pin jointed truss like this. Okay, some force was there here, P, hinge, roller. What is the strain energy stored in the member AB? Strain energy stored in the member AB means UAB. P square L by 2AE. What is the force in this member? AB. So there is a reaction here, clockwise means anti-clockwise. So this is clockwise. So reaction is anti-clockwise. Some reaction will develop like this. HA, this is HB. Clockwise, anti-clockwise. Downward force is balanced by some upward force. Some VA will be there. But at B, see 1, 2, 3, 2 are in line. This is 0. So force in the member AB square into L by 2AE. If force itself 0, strain energy stored is 0. So correct option is D. Okay. Next, third one. In the truss shown in figure below, which one of the following members has no force induced in it? So this problem we solved. Force in the member CF. This problem is something like this. How to find zero forces also I have told you. This point, let us say A, E, F, C. Here force is W. Here also force is W. And this is B. Okay. W was there. Length is L, L, L. Okay. So reactions are how much? VA is W. VB is also W. Okay. There are three ways of finding zero forces in the members. First thing is, at a joint, if two non-collinear members are there with no external load, forces in both members are 0. Second one, if 3 members are meeting, 2 members are collinear, force in the third member is 0. Third one, I told you about the panel shear. If panel shear force is 0 in any panel, force in the inclined member in that panel is 0. See here, there are no 2 members, non-collinear members. So, first one is not there. Second one, there are no 3 members where 2 members are in line. And force in the third member is 0 to tell that nothing is there. Next, panel shear you see. First panel, cut a stand here, VB. VB we know it is W. Second panel stand here, upward W, downward W. Net force is 0. So, panel shear should be 0. So, if panel shear second panel is 0, force in the inclined member is 0. So, force in the member CF is 0. So, that's how quickly, without doing any calculation part, we should complete the problem. So, third question is force in the member CF. CF is C. Panel shear in second panel is 0. So, FCF is equal to 0. Like that we should manage. Next, fourth question. Members of the frame shown below which carry 0 force are. So, this is the truss given. Let us see how to detect 0 forces. This is the roller. This is the hinge. Okay, this is 10 kilonewton. This point let us say D, C, E, A, B. Some angle of inclination 6. This member also was there. 60 degrees, 60 degrees. Okay, now this is the process. How to detect? First, by inspection itself. 1, 2, 3. 2 are in line. Third must be 0. After this becoming 0, now go to C. 1, 2, 3. 2 are in line. Third must be 0. Now when I press it, this compression, these two are under tension. Roller support was there. This compressive force is balanced by this one. This is under tension. So only two members is CE and CA. What are the given? EC only. CE and AC. Correct option is C. Next, fifth one. For the plane truss shown in figure, number of zero forces for the given loading. Now you see this is the problem. Big diagram I am showing. Okay, this is the center line. It's like this. Now 1, 2 things are given. 1, 2 hinges here. This is third one. Then here also 2 hinges. Okay, this is roller. This is hinge. Then here we have inclined members. The central one here, central one here. Now it is connected to the second hinge like this. Okay. Now there went one inclined member connected to second hinge. There went one inclined member. This much symmetry they have maintained. There is one more member here connected, connected. Then there is a horizontal one connected like this. Same thing here. It's connected like this, connected like this. Then here there is one horizontal member, there was an inclined member, there is a load P. Okay, this is the force Q. Second joint there is a Q. Okay, so here there is one horizontal member. Okay, all are done. Now see, number of forces which have 0, number of members having 0 force. How to proceed? Because of P and Q, there will be reaction. Say V2, then this is say some V1. There are two members, two non-collinear members. If there is no external load, these two will be 0, but external load is there. So these two are not 0. Forget about them. Now come to this one. 1, 2, 3. 2 are in line. Third must be 0. Once this is 0, now another 0 will put it with red color. Come here. 1, 2, 3. 2 are in line. Third is 0. Next, this one. 4 are there. We cannot tell. Come here. These two are 0, that's all, but here 3 are there. We cannot tell. Come here. 1, 2, 3, but there is a load here, so it will not be 0. Once this is not 0, this will not be 0. If this is not 0, this can't be 0. If this is not 0, this is not 0, this is not 0. So issue closed. Now here 1, 2, 3, 2 are in line, third must be 0. So half truss we have analyzed. Come here. Two non-collinear members, but external load is there, so these two will not be 0. Come here. 1, 2, 3, 2 are in line, third is 0. Come here. 1, 2, 3, 2 are in line, third must be 0. Next come here. 1, 2, 3, 2 are in line, third must be 0. Now come to this one. 1, 2, 3, 2 are in line, third is 0. Now when these two are 0, now come to joint this one. 1, 2, 3, 2 are in line, third must be 0. Because of this force, this will not be 0. Once this is not 0, this can't be 0. These two also can't be 0. Because non-collinear members, once force is there, will be there here, 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 forces will be there. Now how many are there? 1, 2, 3, 4, 5, 6, 7, 8. 8 members have 0 force. Now what is the option? B. Fifth question, B is the answer. Like that, by inspection, we should be able to get. Next, sixth question we solved in the class. Force in the member AB of the frame shown in the given figure. Force in the member AB, 0. 0 means A. This we have solved in the class. Next, seventh one. The diagram shows a truss subjected to loads as indicated. What is the force induced in the member AB? Force induced in the member AB, whatever way they have given, say, seventh question I'll write here. See, whatever additional loads were there here, there is a roller at this point. Here there is a hinge. This is A, this is B. So wherever you apply loads, here 5, 5. Now at this point there is a reaction like this, HB. Only one reaction at the roller. 1, 2, 3, 2 are in line, third must be 0. So FAB has to be 0. So seventh question, 0 means C. Next, eighth question, force in the member BC. Here itself I'll write. This we solved in the class, force in the member BC. Indeterminate trusses we have given. Because there is this member cannot elongate or contract. Force in the member BC. BC member is kept into fixed hinge supports. That means BC has to be 0. It can neither elongate nor contract. This discussion I have made already. Eighth question. 0. B is the option. Next, ninth. Also we have solved in the class. There are, ninth question you see, when we solved it, there are 3 members, 0 force. See, 1, 2, 3 members, 0 force, let us see. 3 0 force members, what is the option? 2 members tension, wrong. 2 members tension, 2 members compression, wrong. 2 0 force members, wrong. 3 zero force members is D. So ninth question D. Solved in the class. Next, 10th one. Now let us see the 10th question. Now in this case, structure is symmetrical, loading is symmetrical. That means force in the member, support reactions are symmetrical. This is the truss. Okay. Now this is extra. There is a hinge support here. There is a roller support here. Okay. Everything is symmetrical. So there is a load of 50. This point A, B. Height is 1.5. This also 1.5 meters. All are height and that same. So because of symmetry, the reaction, let us say AB is our VC, 50 means 25, VD also 25. Now he wanted force in member AB. Cut it by 1. Angle is 45 degrees. You can see LHS of 1. If I see LHS of 1, this is upward, so arrow mark should be downward. Sigma y 0 plus 25 minus FAB sin 45. So FAB is equal to 25 root 2 kilonewton. Arrow is away from the joint, so tension. 25 root 2 kilonewton tension. So B is the option. Next, 11th one. Force in the member BD of the truss is given like this. Okay, BD. There is a load of 4 kilonewton. 4 CBD. Some loading was given. Now you see 1, 2, 3. 2 are in line. It could have been 0 if this is not there. Now 4 down. So this must be 4 up. Towards joint. So force in the member BD is 4 kilonewton. Arrow is towards joint. So compression. FBD 4 kilonewton compression. Next 12. What is the force in the member BC of the plane frame shown in figure? Okay. Like this is given. Hinge. Roller. This point say A, B, C. 60, 60, 10 kilonewton. Force in the member BC. Now when I am pulling it like this is under tension. This is under compression. This under tension means away from the joint. So here also away from the joint. BC. When I push it like this will support like this. So this is under compression. So this is force in the member BC. 60, 60. This is also 60. So this angle will be 30 degrees, 30 degrees. So from sigma y0 consideration, FAB, FBC must be equal. Otherwise, sigma y0 will not happen. So both of them are equal. One is compression, one is tension. Now apply sigma x0. Arrow mark, this is 60 degrees. This is also 60 degrees. Both arrows are going left side. Minus FAB cos 60 minus FBC cos 60 plus 10 is equal to 0. FAB is nothing but FBC only because of the symmetry. Symmetry in y direction. So this has to be down means this should be up only. So FBC is equal to, I can write 10 by 2 cos 60. So 10 only. BC arrow mark is towards the joint. So 10 kilonewton compression. Cos 60 means 1 by 2. So 10. So FBC is 10 kilonewton compressive. B. 12th question, B is the answer. Next, 13. Simply supported truss is there, 20 kilonewton acting at F. Forces in the members EF and BE. EF and BE. EF is 0 because 3 forces, 2 are in line. Let us see how to resolve the issue quickly. This is the problem. 2 forces are like this. Here 20. Here it is hinge. Here it is roller. 2 meters means 45 degrees. Okay. Now 20 means they have to share symmetrically. This point say A, E, B, C, F, D. Okay. 2 meters, 2 meters and 2 meters. We wanted EF and BE. EF is 0 because 1, 2, 3, 2 are in line, third must be 0. Then BE, B and E, this force he wanted. That means what is the reaction here? 20 means here 10, 10, right? Reactions are 10, 10. Now you see here, this is 0 at a joint, two non-collinear members, no external load. These two are 0, 0. Okay. Now this is 10, upward 10, so it should be downward. How much it should be? It should be F sine 45 is equal to 10. So F is 10 by sine 45. That means 10 root 2 towards, here also towards. So the x component is going right side, so it has to be like this, 10. Away from the joint, away from the joint. So force in the member BE is 10 kilonewton tension. Force in the member EF is 0. So EF is 0, 10 kilonewton tension. 0, 10 kilonewton tension. 13B is the option. Next, 14. What is the force in the member 1 for the structure shown below? So it's like this. So big truss, but we don't have to worry. 1, 2, 3, 4, 5, 6 panels. 1, 2, 3, 4, 5, 6. At third one, it went up. Here, it went like this. Okay. Now this here again one more member went. This is like this. Okay, doesn't matter. Now we'll go up. This will go down. Same thing here also. Down, up, like this was there. Okay. Now here hinge is there, here roller. Everywhere 20, 20, 20. 5 20s. 20 kilonewton, 20, 20, 20, 20. This is 1, 2, this is force in the member 1. We want it in 1. This is 9 meters up to the top, 9 meters. Then 6 at 6 meters. All are 6 meters. 6 at 6, 36 meters. Okay. Now we wanted force in the member 1. See here, symmetry is there. 1, 2, 3, 4, 500 means here it is VA, let us say 50. VB is also 50. First support reactions cut by 1, 1. Look left side. The unwanted members are meeting at A, B is over C. Take moments of all forces at C. Sigma MC is equal to 0. Plus 50 into 6 plus 6, 12. Plus 50 into 12. Minus 20 into 6. This is 0 over. These two will give 0 moment. So you see, clockwise movement is more means this should be now anti-clockwise. Minus F1 into this height is how much from here to here. That we have to find. These angles are given. This is 8 meters. This he has given as 8 meters. So this is anti-clock. Minus F1 into 8, 0. So F1 will get 50 into 12 minus 10 into 12 I can write. This I can write it as 10 into 12. So 50 minus 10, 40. 40 into 12 by 8. 8 5s, 12 5 is 60. 60 kilonewton tension. If you write 20 into 6 as 10 into 12, then 50 into 12 minus 10 into 12 means 40 into 12 only by 8. Without calculator means you have to manage. So you will get 60 kilonewton tension. So simply he has given 60. So 14 is B. Next, force in the member XY. Fifteenth question. Force in the member XY. See here 1 to 4 panels. Take it like this. It's a triangle. Vertical member. Okay. This is P. Here 2P. P. Hinge here. This is X. This is Y. Everywhere 2 meters only. All 2 meters. Height also same thing. 2 meters. 2 meters. That means this angle of inclination is 45 degrees. Okay. Now we wanted force in the member XY. You see, symmetrical loading 1, 2 plus 1, 3 plus 4, 2. 4P. So it has to be, let us say A. VA will be 2P. VB is also 2P. So XY means cut it by 1, 1. LHS, now you see these two unwanted members are meeting at A. LHS of 1, 1. Take moments of all forces about A. Sigma MA is equal to 0. Now you see, cut here, look left side. 2P up, this is P down, these two will give 0 moment. Unwanted members are meeting here. Okay. Now these two will give 0 moment. This is also give 0 moment. This is clockwise. To balance a clockwise movement, it has to be anti-clockwise. This is Fxy. Let us call it as Fx. Now you see, clockwise, anti-clockwise balances. Now where to replace this Fx, or F1 we will call it. This force I can replace wherever I want from the principle of transmissibility. So this, if I keep it here, this is F1x, this is F1, F1y, F1x. See, F1x will give 0 moment, headache is gone. So plus P in this length is 2 meters, plus P into 2 minus F1y. Only F1y is how much? F1 sin 45. So F1 sin 45 into 4. F1 sin 45 into 4. Other members, when you cut it, this and this, they will give 0 moment about A. So headache is gone. These two members, 3 members we didn't cut, so no forces. So you have to consider only these two forces. This force I will replace here. What's the advantage? X component will give 0 moment. I can replace here also, then XY components, both moment I have to find. That's why I told you, you must learn, or you must remember that principle of transmissibility. A force can be replaced anywhere along its line of action. Its external effect remains the same. So that means equilibrium equations remain same. Sin 45 into 4 is equal to 0. So F1 is equal to 2P by 4 sin 45 means 1 by root 2. So 1, this is 2 by root 2 means P by root 2. Right? 2C will get it, root 2. So P by root 2, arrow mark is towards the joint, compression. So Fxy is P by root 2. What is the question? P by root 2, compression. So 15th question, B is the answer. Next, 16th. All members have same cross-sectional area. Bending resistance of all the members is small in comparison with their axial force resistance. Okay. All the external loads are applied directly or indirectly at the joints. All joints are idealized to be frictionless. Which of these are assumptions made in the force analysis of simple trusses? Force analysis of simple trusses means method of joints or whatever it is. All members have same cross sectional area, not necessary. It can have different cross sectional area also. So one, remove it. If you remove one, AC gone. Next B and D, 2, 3, 4 or 3, 4. Next, our point is bending resistance of all members is small. That is correct because bending resistance is small. You are taking a member, a rod or a bar or a link. When applied bending moment, it will not take. So its resistance to bending moment is 0. We will take it. So second one, there is no bending moment at all in the first place. Resistance also is small, we assume. Okay. So 2, 3, 4 are correct. Okay. Bending resistance of all members is small when comparison with their axial force resistance. Those members axial force it can take so high, flexural resistance is very less. Okay. That means you don't apply any moment at all on the members. So 2, 3, 4 are correct. 16B, bending resistance is small, so they won't take any bending moment at all. Next, 17. A pin jointed truss loaded as shown in figure. Okay, now we have to find what are the forces. This is 30 kilonewton. This is 10. A, hinge, B, C, D. This is E. 2 meters, 2 meters means angle is 45 degrees. He is asking member AB, AC, BD, CD. 4 member forces we wanted. Which member has 0 force can we detect? See here, no member has 0 force. These two will have forces, force is there, here force will be there. Because there is a reaction, forces in these two members also will exist. So 0 you eliminate, then can we get without calculation? See here, 3, wherever 3 is there you remove. It's a 45 degrees. There is a roller support here. See here, this point, if this is clockwise, here anti-clockwise, this is VB, this is VSA. Now in this case, at B, there is a roller support, this is third. Only one reaction possible. 1, 2, 3, 2 are in line, third must be 0. So FA, member AB must be 0. Member AB 0 means A3. A3, but A and C, two options are there. Then B2, B4. B is what? Member AC. Member AC, if I want to find, cut here by 1, 1. Now look up. These two, we don't want these two members, they are meeting. If I want member AC, unwanted members are these two. They are meeting at D. So take moments about D. This is 2 meters. This is also 2 meters. Now you see, if I cut here, this is how you have to manage. All forces we should not solve them. Cut it by 1, 1, FAC. Cut it by 1, 1. Then upper side of 1, 1. These two are meeting here. So moments of all force about D is equal to 0. Tail to the head towards the clockwise, so it has to be anti-clockwise because this will give 0 moment. FAC, this is 2 meters, 2 meters. So plus 10 into 2 minus FAC into 2, 0. So FAC must be 10 kilonewton. Tension. See, FAC 10 kilonewton, where is there? 10. See, A3 correct. Then B2 he has given 50 wrong. So B4 is 10. So FAB is 0. AC is 10. That means this is A3. This is B4. A3, B4. Enough. It's over. All others waste of time. A3, B4 means C. 17th question, C is the answer. Other forces we don't have to calculate because you are pressed for time. So that's why when even they are giving you 4 members, this how we have to take. First option, first force is how much? How many options are tallying? 2 are there. Then find the second force. Then how many options are matching? Only one, close it. Next, 18. 3 equally inclined members of a plane frame having tensile forces respectively are jointed at a point. Relationship between P1, P2, P3. Equal inclined frame means Lami's theorem that we have learned. If they are equally inclined means 60, 60, 60, 120 degrees say. P1, P2, P3. These are equally inclined 120, 120, 120. If angles are same, the forces must be same. The relationship between P1, P2, P3, both of them are equal. P2, P1, P3, P1. So D is the correct. From Lami's theorem we have studied. So P1 by sine 120, P2 by sine 120, P3 by sine 120. So P1 is equal to P2 is equal to P3. It's like this. P1 by sine 120, P2 by sine 120, P3 by sine 120. So you will get P1 is equal to P2 is equal to P3. That's the meaning there. Okay. So that question is D is the option. Next, 19th. Consider the following truss. Force in the member CF. CF we want to find. So this is CF. We'll draw the diagram. 19th question. 1, 2, 3, 4. 4 panels. Okay. Center. This went like this. Like this. This went this way. This way. Hinge. This point you take say A, B, C, D, E, F, G, H. See here in this direction there is a force of 25, 50, 100, 50, 25. All are inclined 4, 4, 4, 4. Angle of inclination 45 degrees. Okay. So is acting in the same line means is also 45 degrees. Perpendicular that is acting. Which member we wanted? Force in the member CF. CF. This force we wanted. Okay. So what we have to do? Force in member CF means cut it by 1, 1. RHS of 1, 1. No need to find reactions. VE has given. So when we wanted CF, unwanted members are these two. These two are meeting here. So when you stand here, look right side. These two will give 0 moment. This is giving anti-clockwise. So this should give clockwise. That means this way. This already 0. 1, 2, 3, 2 are in line. So they should match. Force in the member CF. 50 kilonewton, that's all. Directly we can write because they are in the same line. 45 degrees compression. 50 kilonewton compression. Cutting etc. is not required. 50 kilonewton directly has given. Compression tension, you didn't worry. A. Cut right side also not required because these two are in one line. Perpendicular to that is this one. So these two will not come in this picture at all. So once this is 0, 1, 2, 3, this will be 0 if this load is not there. But this is there. To balance this, these two will balance this way, and this will not come into picture in this direction at all. So force in the member CF, they balance themselves 50. Next, question number 20. This question matrix methods I have solved. Stiffness matrix method. We found that P required is, what is the horizontal displacement? Delta AX. We have solved it as P by 1.5 into Z we have written. That Z has given it as 1.5 K, that's all. P by 1.5 K. That means D is the option. This we solved in the class. Next, 21. Suresh. Now see the 21 question. There are two diagrams wherein they have shown in the first case like this. Both are hinged supports. Circle is there, so hinge. Here also circle. So you have a force P. Angle of inclination is theta. Okay. This is the first case, X case. Okay. Length is L here, A. This point is B, C. Both of them are under compression. What equal force must be there? This is FAB sin theta plus FAB sin theta. Both forces will have to be equal because of the symmetry in the y direction. Both have to be compression. X direction they will balance. So this force, let us say, you can call it as some Q. This also must be Q. Q1, let us call it. Q1 sin theta, that means 2Q1 sin theta must be equal to P. So Q1 is P by 2 sin theta. Some value will get. So sin theta value, as theta increases, we know that sin 90 is 1, sin 0 is 0. As the angle of inclination increases, sin value also will increase. Sin theta value will increase. Now that value is in the denominator. That means as theta increases, sin theta increases, Q value decreases. So for this case, some theta he has given. Now second case, what they have done, that theta is reduced. Like this they have kept. Fix hinges here. Same load P. This is Y case. Okay, this is theta by 2. Now this is force Q2, let us say. Same force will be there. Now Q2 you will get P by 2 into sin theta by 2. So theta, sin theta by 2 is sin theta by 2, as it decreases, its value also decreases from 1 to 0. That means this value compared to this value is less. If this is less, Q2 is more. So we can say that Q2 is greater than Q1. Forces are more. If force is more, deformation is more. That means deflection is more. Delta in the second system, this delta X system you take it, delta X system some value. Delta Y system, this is Y system. Delta Y is greater than delta X. Why? If force is more, deformation is more. Correspondingly, deflection also more. So in the second case, force is more, deflection is more. Okay, when compared with the first case. Now let us see what are the options. X will have more member force. Wrong. First, there itself wrong, leave it off. X will have more member force again, wrong. C, X will have less member force, correct, because Qt is greater than Q1 means, so Q1 is less than Q2. This is X system, this is Y system. Force in the X system is less than Y system. So X will have less member force and more deflection. More deflection is also wrong. Then that means delta X, this is X system, this is Y system. Here also delta Y we have taken, delta X is less than delta Y, or delta Y is greater than delta X. Any which way we can write. This corresponds to X system, Y system. Forces deformations are less. Now you see, C bit is X will have less member force, correct, but more deflection is wrong. D you see, less member force, X will have less member force, correct, and less deflection at B compared to Y. See, compared to Y, less force, less deflection. So correct option is D. This will have more force, more deflection. This will have less force, less deflection. So X will have less member force and also less deflection at B when compared with Y. Correct. So D is the correct option. Next, 22nd. That means this idea we should have, as theta decreases, what happens to the force or theta magnitude? Theta magnitude decreases, but that value is in the denominator. Denominator value decreases means this one will increase, Q2 will increase. That's how you have to analyze, but you have 2 minutes time for that. 22. A pin jointed 2D truss is loaded with a vertical force of 20 kilonewton. This we solved in the class. Horizontal force at joint B as shown in figure. Force in the member BC. Force in the member BC he asked. This problem we have solved it already. Why one member force? We can calculate all member forces also, like that I have told you. This was there. This is 20 kilonewton. Okay. Here left side is also 20 kilonewton. This is a hinge support. And here overhang. And here it is continuing G. This force is G, E, D, C, B, A. This point is F. All distances are 5 meters, 5 meters, 5 meters. This is also 5 meters. Height is also 5 meters. Now question is force in the member BC. Okay. First reactions we will find. This is VA. Okay. HA is this way. To find VA, take moments of all force about A. 20 clockwise, 20 anti-clockwise. Since these two are balancing, here vertical reaction VG is 0. Then HG is 0 because it is a link. As I told in the class, 1, 2, 3, 2 are in line, third must be 0. Now after finding the reactions like this, now you can cut these two are 0. This is down 20, so VA must be 20 kilonewton up because no other way allowed to balance. Left side 20, so right side 20. Now we wanted force in member BC. There is one inclined member also, FCF, like this. Now we wanted BC member. Cut here. You will cut here and look right side. See here. Cut, look right side. Is there any force? No force. So force in the member BC is 0. So BC 0 means 22A is the option. Next 23 solved in the class. I think both the positive you got it, right? B is the option, we got it. We got upward negative means both are positive. This is we solved in the class. In the matrix methods I have completed. Next 24. Okay, now we'll see the 24th question. Zero load test indicate whether a plane truss is geometrically unstable. 24D is the option. Zero load testing is done to check the geometric stability of the trusses. So what it is? For what type of trusses we check the uh, we go for the zero load testing. First we will see what are the types of trusses. We have basically three types of classification is three types of classifications. First thing is what we have solved are simple trusses. Some compound stresses are compound trusses also are given, and one complex truss also we have solved. So we didn't mention the names, but simply we solved them. Now let us classify the trusses, and for which type of trusses we have to go for the zero load test. Okay, so we have now classification of trusses. First one is simple truss. Second type of classification is compound truss. Third is complex truss. Simple truss means, as I told you, what we have calculated, we have done was simple trusses. M is equal to 2j minus 3. First one triangle will form, stables one. Then for each additional joint, two members are attached. If you make the form, if you make it triangles like that, we get a stable, triangulated, determinate truss. Such trusses are called simple trusses. Okay. So first one is simple truss, which follows M is equal to 2j minus 3. Triangulated form. Okay. Now, if you take the examples, I have given you one example also. You form a triangle, then one more joint, okay, like this. All triangles we have formed, simple truss. Not necessarily triangles, you can make it like this also. Okay. First, you build this triangle, let us say. This triangle you built. Next, this one, when you are building it, you make it like this. Okay. Next, you extend this one. One more joint you want to make it here. One member here, second member here. Still it is stable only. This becomes simple truss. Next, compound truss. Second classification is compound truss. Compound truss. It is formed by connecting two or more simple trusses. If you connect two simple trusses, you will get a compound truss. How to connect? By a common bar or three members you can take it. Two trusses can be connected by three bars or a single bar, like that. So now let us see how to connect. We have a this is how you have formulated one single truss. Let us say hinge support is there. This is a simple truss, triangle, another triangle. Take another such simple truss, we will take it, connect it here. I will take now an independent truss like this. Okay. This is another truss. Okay. This is another truss, let us say. Another triangulation we formed. One like this. Black color one is a simple truss. Blue color one is a simple truss because they are connected. They are made up of triangles. Connect them by a common bar like this. Common bar or a common joint. Connect them, it becomes like a compound truss. Okay. Now another example is, this is a compound truss. One example we have solved earlier, this one, to find the stability. Black color one is one triangular truss. Okay. Another one we have calculated, we have taken, this is one simple truss. Another simple truss is say like this. Black color one simple truss. Blue color one is another simple truss. These two trusses can be connected by three bars. 1, 2, 3. Like this you connect, say, two trusses. Then it becomes a compound truss. Compound truss. Okay. The truss, now it is a common bar. So this is blue truss is joined by three members to another truss. So either by three members or a common bar, if you connect them like the two simple trusses, it will become a compound truss. Okay. Next, third one, large trusses. Supposing that I will draw here itself. We have a very big truss is there like this, say. This is actually the truss. This is the main truss. Okay. This black color one is main truss. But if it is taking too much of heavy loads, let us say, what we do is, this member we replace it by another truss like this. Another simple truss. See, one triangle, another triangle. So this is blue color one is a simple truss. Here also, this also you find it big, let us say. You connect it by a triangle like this, triangle like this. Same thing, I can replace this one by a small truss like this. This is simple truss. Also called secondary truss. Main truss, black color one, these are secondary trusses. So simple trusses are connected to form another truss. Then it will become compound truss. If you cannot classify a truss as a simple truss, as a simple truss or a compound truss, then such trusses we call them as complex trusses. One complex truss problem also we have solved, where complex truss we have taken where all the joints have minimum of 3 members, but because the loading was symmetrical we could break that problem quickly. But if they are not symmetrical, you have to solve the all simultaneous equations. It takes a lot of time. Complex stresses means it will take all simultaneous equations. We have to get it and we have to solve it. I said such trusses we call them as complex trusses. Which those are the trusses which cannot be classified as simple or compound. So that is third one. Third type of classification is complex truss. Complex truss. It is the one which cannot be classified as simple truss or compound truss. Or compound truss. Example, supposing this what I have given you earlier. This member is like this, say. This is connected like this, like this. Then this is the pin, this is also hinge. If two hinges are there, vertical member not required. This is complex. Or if you want to put hinge, let us say, this depth should be different. This depth some d, let us say, from here to here, this is says d dash. This can be taken another like this. This is hinge here. I want to keep a roller here, say. Then I have to add, two members are added. One more member I have to make it like this. It should go this, through this it will go, let us say. No joint here. No hinge. So this is a B. This point also let us say D. This depth let us say D dash. So this is also a complex truss. Another complex truss I have given you was earlier like this. This is also a complex truss. M is equal to 2j minus 3 satisfies, but no triangles will form. So this way you connect it, let us say, then it will become complex. This we have solved. Such cases where complex trusses are given, whether it is stable or not, though m is equal to 2j minus 3 is satisfied, we cannot predict whether they are stable or not. We have to go for the analysis itself. Such cases where by inspection itself you cannot find whether it is stable or not, by inspection you cannot find whether it is stable or not, is for a case of complex trusses. So for complex trusses, to determine whether it is stable or not, you have to go for the zero load test. What is the zero load test? Supposing that external load we don't apply, you take this member force, let us say some 10 kilonewton, you take it, but externally no loads are there, some 10 you take it, then joint by joint you analyze, and still it is in equilibrium, let us say, then it is unstable structure. That means if you take 20 also, it will be in equilibrium. No load is there. What is the thing? When external loads are not there, forces in the members must be zero. But if you take 10 also, it will be in equilibrium. 20 also you take it, it will be in equilibrium. That means they are unstable. They will become unstable if d and d dash are equal. If they are not equal, they are stable. So that is called, if d becomes d dash, that is called critical form. At that position, because of the geometry of the truss, it becomes unstable. That's why zero load testing is done to check whether the truss is geometrically unstable or not. Okay. So this is our one complex truss we have taken. Two examples now fresh I am giving. This is called hexagonal truss. I told you in the zero load testing some hexagonal trusses, to determine whether they are stable or not, we go for the zero load testing. Okay. So three types classification. All we have solved, but we didn't mention them, that what type of truss they are. Okay. So these are the conclusions, or not we write. What we have done was to check the stability of compound trusses, how they are connected we have to see. To determine the stability of a compound truss, what we have done? One compound truss we have taken in the stability of structure trusses. Compound truss, it is necessary to identify the way in which simple trusses are connected together. What we have done? See, this type of trusses we have taken, one compound truss. Inside this one, we have drawn one more truss. This is a compound truss. Right, this type of problem I have given. This point, let us say A, B, C, D, E, F, where they meet is G, say. This is compound truss. How they are connected together, you have to see. The blue colored truss is connected by three links, those three links are concurrent at G. That means rigid body rotation will take place. Compound truss unstable. This is what we have taken. Another compound truss what we have taken. Like this I have given without changing the colors. Simple truss. Next another simple truss. So two simple trusses connected by three links which are parallel. See, three parallel. This is a compound truss. Unstable. Why unstable I have given already. Two trusses are connected by three parallel links. So rigid body translation, rigid body rotation. Okay. Next. Now this is the case we have already done. Three links are parallel. Three links are concurrent. This type of by inspection itself finding whether they are stable or not in the case of complex trusses not possible. So we have to go for the zero load testing. Next, this is the first point. Let us see now the second point. Note 2. Now we have seen if you have a simple truss or a compound truss, by inspection itself we can detect whether they are stable or not. But for the case of complex trusses, we cannot identify by seeing them. So we go for the zero load test. That we see as a second point. If a truss is identified as complex, then it may not be possible to tell by inspection. To tell by inspection if it is stable or not. In the earlier example, this is what I gave you. This is a hinge roller. Connect it like this. This also it should go through this one only. Okay. No joint here. No pin. Because I didn't put any circle here. This height, let us say some D. This height say some D dash. If D is not equal to D dash, stable. If D is equal to D dash, unstable. Like this. This is hexagonal truss. So because it is in the shape of hexagon. So how to conduct? Third point. To check whether it is stable or not, we conduct zero load test. Whether it is geometrically stable or not. Zero load test. So in this test, this I am explaining how we have to do. We do not apply any load on any joint. Okay, any joint. So theoretically, member forces should be zero. But we assume a fictitious value. Fictitious value, say 10 kilonewton. In any one member of truss. Then analyze entire truss. Joint by joint. At the end, what will happen? Supposing that this 10 kilonewton you assume, then find these two forces. Find this, come back here again, 10 equilibrium satisfies. So at the end, when we approach to the initial joint, we find that equilibrium equation is satisfied. Such trusses are classified as unstable. Are classified as geometrically unstable. That means M is equal to 2J minus 3 satisfies. Number of minimum 3 reactions are there, 3 reactions will be there. Those 3 reactions are non-parallel, non-concurrent. But still it is unstable because of the geometry of the configuration of the members. Complex trusses case, they will become unstable. You will know only by after the analysis only. Now we find that if this and this are equal, it is unstable. If this and this are not equal, then it becomes stable. So at that, once they are equal, such a critical form, it won't be stable. Any value take it without load also, zero load is there, but assume some force 10 kilonewton, analyze them. Then all entire equilibrium is still satisfied. It should be some eccentric, that means um, the inconsistent results should be there. No inconsistency. Again, equilibrium is satisfied. That means it is unstable structure. Okay. So that's about the zero load testing. We do it for complex trusses. Other cases by inspection, already I have told you how we have to make it. Next, 25th. A cantilever pin jointed truss carries one load. This is the truss given. Okay. Then one member came like this. This is like this. Then this is one member went this way, slightly less, comes like this, comes this way, or slightly up, whatever way they have taken, some slope was there. Okay, like this. like this. Okay, A, this is D, B, C, G, Z, and some load P was there. This is the structure. It is a cantilever pin jointed truss, carries one load P at the joint Z as shown in the given figure. The hinges in the vertical bar at A and D, okay, the truss has only 3 horizontal members, fine. The nature of the force in the member AB. What is the nature of the force? How do you find? First of all, how do we find forces in the members? We'll cut AB by 1, 1, fine. RHS of 1, 1. Unwanted forces are these two. If you extend these two, they will meet somewhere here. Not necessarily at G, somewhere here, some X, let us say. Okay. So if I take on the right side, take moments of all force about X is equal to 0. So stand here, look at P, tail to the head towards this one, clockwise. To balance that, it must be anti-clockwise because these two are already giving 0 force. So anti-clockwise means like this. Now this is clockwise movement about X, this is anti-clockwise movement about X, some point in air. So arrow mark towards joint. So FAB is compressive. You are given 2 minutes time for that. Okay. So this value, nature of force in member AB is compressive. So 25C. 26. Axial force in the member BC. We have given it is 30 kilonewton, means force in the member BC is same 30 kilonewton, solved in the class. There in the class what you have taken was, instead of 30 kilonewton I have taken 20. Now they have given 30, that's all. Other than that, no difference at all. Alpha is, now I have given you 30 degrees. Whether alpha is 30 degrees or whatever it is, here he also has given 30 degrees, so same. So you will get 30 kilonewton. So 26, D is the option. 27 we solved in the class, 173 kilonewton. So 173 means 27C. This also solved in class. Matrix methods we solved in class. This is matrix methods. This is method of sections. Next, 28. How is a truss which undergoes rigid body translation? Rigid body translation means reactions are parallel. It will happen only when insufficient number of reactions are there. It is a truss. Truss means simply supported truss. So statically unstable truss, 28C. This also I solved in class. Next, 29. In pin jointed truss shown in figure, horizontal deflection of roller support will be the sum of deformations in the members AG and GF. See here, there is one truss like this. Okay, it's connected this way and this way. So whatever may be the loads, 5 kilonewton, 10 kilonewton, even the loads are in a different way also, same thing. This is 5 kilonewton. This and this. This point is AG, AG, GF, BCD, BCD. Horizontal deflection of roller support. Supposing that AG member elongates by 10 mm, CF, GF member contracts by 2 mm, let us say. So 10 minus 2, 8 mm, it must go right side. Otherwise, the 10 mm elongation, where will it go? Whatever sum of deformations are there, that net deformation, whatever you get for AG and GF, to that extent it can go out or in. If two members are contracting, let us say 5 mm, 5 mm, then F will go in by 10 mm. If this elongates by 5 mm, this also elongates by 5 mm, then this will go out by 10 mm. If this elongates by 5 mm, This elongates by 0 mm. Then 5 plus 0, 5 mm. Like that. So in this way, AG plus GF deformations are the horizontal deformation. Let us see pin jointed truss shown in figure. All two members they have given, you see. Only if they say AG, let us say. For this loading, GF member force is 0. Force is 0 means deformation is 0. Well, that means 0 deformation. This is 5 mm, say. 5 plus 0, 5. Otherwise, if they give this moves by horizontal displacement of deformation, the AG, then that also is correct. But he has given minimum two members, then accordingly we have to select. AGGF. You see here, where is that AGGF? If GF is not there, only AG is there, then also that is correct. Because GF force is 0, then deformation is also 0. But that way they didn't give you the option. 5 plus 0 or 2 plus 0, whatever it is, you should write that way. So AG plus GF means C. Like that, whatever AG member elongates, so amount, if it elongates by 5 mm, then F cannot stay there only. How to accommodate that elongation? To permit such free elongation, rollers roll out or roll in. Okay, so that again additional deformations because of the support reactions should not develop. It is a statically determinate structure. Any deformations happen, rollers roll out or they roll in. Next, 30th one. Cantilever truss as shown figure. What are the magnitudes of axial forces in the members 1, 2, 3? 1, 2, 3 they have given. See, third force AC, it has to be 0. One hinge, one roller. Forces in the members 1, 2, 3. 1, 2, 3. Third force must be 0. No option is there. So in this case, third member has to be 0 force, but he didn't give you anything about that. That means printing mistake somewhere. Third member must be 0. This they have written 1.00p. Now we will calculate how much they are, then accordingly you will answer. We will correct the question. Okay. So this is the problem. You have a load P. This let us say hinge. This let us say roller. Okay. So there is a hinge support here. There is a hinge. Okay, it is like this roller. Here it is reaction. This length is theta is tan inverse 3 by 4. Tan inverse 3 by 4 means 36 point some 87 degrees. 3 by 4 means this is 3 meters, 4 meters and this is 5 meters. Then only theta will happen like that. So now let us see how to manage. Here there is a downward force. To balance it, upward force here only should develop. This point let us say ABC. A, B, C. Then vertical reaction at C must be P. Here no reaction. P into 4, this is clockwise couple. To balance it, anti-clockwise couple should form. How much? Same amount. So P into 4 must be equal to X into 3. So that means 4 by 3 means 1.33. HA is equal to 1.33P. HC is also 1.33P. So 1.33 into 3, that means 1.33 means I can take it as 4 by 3. 4 by 3 into 3 is 4. P into 4 is 4. Now let us see. Coming to this point. Okay. See 1, 2, 3, 4. We see upward. So it has to be downward. So force in the this is the third member he has given. Third member is P. Towards the joint. Towards the joint. Okay. Third force is P. That means B and D, two options are there. Then that means you have to calculate. This is downward, so it has to be upward. Force in the member AB. This he has taken it as 1. FAB sin theta is P. What is FAB? FAB is P by sin theta. P by sin theta means 3 by 5.6. So P by 0.6. So 10 by 6 means 1.40 means 1.66p. So FAB is 1.66p. Let us see with 2 it will match. So 1.67p, first member, third member is P. So naturally it will be away from the joint, then towards the joint. It will be 1.33p only, we don't have to check. 2 are over. So first member is 1.66, B, 2 is 1.33, C is 1. So B is the correct option. We have solved so many problems where this hinge was here, this roller is here. Then 1, 2, 3, 2 are in line, third will be 0. But in this case, here hinge is there, here roller is there. So all three members will develop the force away from the joint, away from the joint. You see, this is downward force. The y component of this will be balanced by this one. These two will balance themselves. Roller will have no vertical reaction. Okay, sigma y 0 can be satisfied with these two itself. So correct option is C, B, because 2 points we found. This and this, once you find it, other things are not required first of all. Otherwise sigma x 0 you can write. If you write sigma x 0 minus 1.66p cos theta plus force in the member BC is equal to 0. You will get force in the member BC 1.33p. Next, 31 we solved in the class. You get around 30 mm. Which chapter? Deflections of trusses chapter. Next, 32. See here, there is a truss like this. This is a square type. There is a roller here. Assume that roller I am showing like this. Here also there is a roller. What means a rigid jointed one kept on roller, let us say. And here there is one inclined. This is how it is running. Okay, there is a hinge support. P, Q, R. Okay, actually there is one member missing, but that is compensated by one additional vertical reaction at Q. So it is stable. This is 30 kilonewton down. That's all. Okay. So now there is no horizontal action. See here, that means HP is equal to 0 here because there is no action. Then VP, vertical reaction at P, you have to take it. Some force is there, say. Okay. Now, that 3 meters, this is distances are known to us 3 meters, 3, 3. This height is 2 meters. Okay. Since there is no horizontal action, horizontal reaction must be 0. Okay. Now let us take moments of all forces about one. Which point is better to take moments? If I take vertical reaction at R, okay, there are 3 members here, x, y components also there can exist the forces. There is only one vertical load 30 kilonewton. The correct combination of reaction at P, Q, R is given by PQR is given. Vertical reactions only we have to take it. If this height is 2 meters, 3 meters, this height is 1 meter. From here to here, this height is 1 meter. So, if I take moments of all forces, there are 1, 2, 3 vertical reactions are unknowns. We will take like this. Cut it by 1, 1. Like this. Cut it by 1, 1. Okay. Look left side. When you look left side, this force and this force are horizontal. That means they will not give any vertical component. So, left side if you see 30 down, to balance 30 down, here it should be 30 up. Cut it by 1, 1. Then take LHS of 1, 1. You can apply sigma y0 plus Vp minus 30 is equal to 0. So, Vp has to be 30 kilonewton. Okay. Now, you see Hp has to be 0 because there is no couple. Now, this is a clockwise couple. To balance it, anti-clockwise couple should be formed. That couple will develop like this only. So, Vq must be down. How much? Distances are same. So, it has to be 30 kilonewton. This also has to be 30 kilonewton. This can only give anti-clockwise couple because there is no other fellow who can give the anti-clockwise couple. So, PQR, correct PQR, P is plus 30, minus 30, plus 30. So, B is the option 32. So, how quickly we get the idea that we have to cut it, look left side, then how to find Vp. After finding Vp, then it will form a couple 30 and 30, then it should be anti-clockwise couple. Otherwise, sigma m will not be 0. So, that logic we should get it. So, Vp is 30. So, clockwise couple should be balanced by anti-clockwise couple. So, Vq is equal to minus 30 means downward, Vr is equal to plus 30 kilonewton upward, like that. So, this will balance. So, 32 is over. Next 33. This is like assertion and reasoning type.